So, good morning, good afternoon, or good evening, everyone, depending on the location. I'm Koji Yamashita, the moderator of today's webinar from UC Riverside. I'm serving as the PS chair of the IEEE Footage section. First off, welcome to the IEEE PS Footage section webinar. Our footage section spans a wide geographical area stretching from West Covina to the eastern edge of California and from Temecula to Baker. Today, we are honored to welcome a special guest from China, Professor Jinyu Wang. He will be talking about a topic that's becoming a significant concern around the world, meaning cybersecurity in the power grid, with a focus on the false data injection attacks on measurements. Thank you for joining us, Dr. Wang. And before we begin, let me give you a brief introduction. Dr. Jinyu Wang received both his bachelor's degree and PhD degree in electrical engineering from Huazhong University of Science and Technology in Wuhan, China in 2015 and 2021. He is currently an assistant professor at Huazhong University of Science and Technology, working in both the School of Electrical and Electronic Engineering and the School of Cyber Science and Engineering. From 2019 to 2020, he was a visiting scholar at Virginia Tech University in the United States. His research focuses on applying artificial intelligence (AI) to power systems and improving cybersecurity in the power grid. And with that, Dr. Wang, the floor is yours. And then let me stop. Yeah, please start.
Okay. Thank you very much, Koji, for having me in this webinar. Hello, everyone. My name is Jinyu Wang, and I work as an associate professor at Huazhong University of Science and Technology, or HUST, in China. And today I will present our recent work on detection and recovery of malicious power system measurements under false data injection attacks. This research aims to address some critical cybersecurity challenges in modern power grids. So, to begin with, please allow me to. Actually, Koji has introduced me, and I just give a quick summarize. I hold a Bachelor of Engineering and a PhD degree in Electrical Engineering from HUST, and my postdoc focused on cyber science. And since 2024, I've been an associate professor. As you can see from my experience, I mainly focus on the interdisciplinary study of electrical engineering and cybersecurity. This is the outline of today's presentation. I will start from the research background. As it's happening around us, the ICTs used in power grids are evolving from isolated and proprietary to open and non-proprietary, introducing severe risk of cyber-physical attacks. So what is a cyber-physical attack? Actually, a pure cyber attack mainly aimed at causing damage to the information availability or the information assets. However, in a cyber-physical attack, attackers usually desire to use cyber attacks as a tool to disrupt the operation of a physical system, such as the power system, to cause very serious economic and social losses. The vulnerabilities that can be exploited to launch a cyber-physical attack exist in different layers of an ICT system, such as the hardware, firmware, software, or communication layer. The Ukraine blackout in December 2015 is known as the first blackout directly caused by cyber attacks. This incident has greatly elevated the attention of academia and industry to the power grid cybersecurity. So false data injection attack is a representative cyber-physical attack. Its target is the state estimation application widely deployed in power grid control centers. The attack goal is to stealthily change the results of state estimation so that so as to mislead system operators into taking erroneous control actions. This goal can be achieved by tampering with a carefully selected set of electrical measurements collected from SCADA or WOM systems. To defend against FDIAs, many research has focused on the detection of this attack. The existing method can be roughly divided into model-driven and data-driven categories. Model-driven method detects FDIAs based on some manually defined rules. The rules often need to be constructed in a case-by-case manner with the detection criteria changing from one power system to another. In other words, the detection rules are system-specific. Developing such rules usually need prior knowledge of the topology and parameters of the power grid. In contrast, data-driven methods do not require manual creation building, manual criterion building, and thus do not require detailed power system parameters. Data-driven method detects FDIs by identifying abnormal feature patterns of power system measurements. With the rapid development of AI, machine learning-based methods have become a mainstream data-driven method in recent years. Machine learning-based detection methods train a learning model to distinguish normal and abnormal measurements. Once the offline training is finished, the parameters in the model is usually kept invariant. However, the operational state of power system is changing from time to time. The integration of renewables and smart loads increases the probability that the power system operates at unusual working points. Meanwhile, the topology of the system can change at any time because the planned maintenance or unforeseen contingencies. So when training a machine learning model, we want the model to see as many operational states as possible so that it can make correct decisions no matter how the power grid state changes. Unfortunately, the training data is often collected via biased sampling. The so-called big data is big in volume but small in representative capability. Rare statistical models may be overwhelmed by dominant models. So when the model is trained using data collected under a specific operational state, but the system evolves into another state after the learning model is put into operation, the detection accuracy may significantly degrade. This problem is known as the concept drift. It is a key challenge of existing machine learning-based FDIA detection methods. Besides FDIA detection, many researchers also studied the recovery of power system measurement to defend against FDIAs. FDIAs can only be launched when some measurements received by power grid control centers have been maliciously modified by attackers. So if we can detect such modification and replace those data points with the AI recovered data, the impact of FDIA on result of state estimation can be significantly limited. In addition to FDIA recovery, these studies can also be used to reconstruct lost data points. So common data-driven malicious power system measurement recovery methods include interpolation, low rank-based method, and machine learning, and so on. So these methods usually have linear approximation assumptions or low rank parameters whose robustness is relatively poor. Moreover, the strong randomness of renewables is not taken into account in these methods. Thus, when facing measurement patterns with high non-linearity and strong randomness, existing data recovery methods often have poor performance. So in this webinar, I will introduce two recent papers from my lab. The FDIA detection paper aims to address the concept drift challenge by introducing a new machine learning paradigm called dynamic neural network. And the data recovery paper uses a diffusion model to decrease the reconstruction error under complex data patterns. But before we dive into the two papers, I'd like to give a brief introduction to FDIA because I think not every audience is very familiar with this concept. As I mentioned, FDIA is a cyber attack targeting power grid's state estimation. So let's quickly review the related concepts. Given the configuration of a power grid, the branch power flow, branch current, node power injection, and node current injection variables can be calculated using both voltage magnitude and phase angles. So voltage magnitude and phase angles of all buses can be selected to form a set of state variables to characterize the operational state of the power system. In practice, not all state variables can be directly measured. For example, compared to voltage magnitude, phase angles of buses are much more difficult to be measured. Besides, the measurement process will inevitably introduce errors. So how can we obtain a complete and accurate set of state variables in practical power grids? The answer is to conduct state estimation. The key idea is to make use of the redundant measurements deployed in the system to estimate an accurate set of values of state variables. Among all the mathematical principles, weighted least squares is the most widely used state estimation algorithm in today's power grids. So let's see a simplified version of weighted least square state estimation, that is a linearized state estimation. We can see that the state estimation results the result denoted by x with a hat can be computed by a linear operation of the measurement vector of D. So here is the H is the measurement Jacobian matrix, and W is the diagonal matrix of weight, whose elements are the reciprocals of the error variances of the corresponding measurement. That is to say, more robust measurements tend to have higher weights in W. So weighted least square state estimation is very sensitive to outliers. Gross errors in the measurement vector Z may lead to very large deviation in the state estimation result. So in practical power system, gross errors can be introduced in the measurement and communication process due to measurement device malfunctioning or communication errors. Before conducting state estimation, bad data in Z must be detected and identified. Common bad data detection criterion is based on the residual. After we compute the state estimate, we need to validate it by computing the residual vector R. If the magnitude of R is less than the predefined threshold, we can accept the state estimation result as it indicates that no bad data exists in D. Otherwise, if we need to iteratively remove some element of D and double check the residual vector until all the bad data in D is identified. FDIA is exactly making use of the vulnerability of this residual-based bad data detection. Suppose that an attacker intends to inject an attack vector A into the measurement vector D. As long as the attack vector A has a structure of A equal to H times C, where C is an arbitrary vector, the manipulated measurement D will not trigger the residual-based bad data detection, as the attack does not change the value of the residual vector D. Here is the residual of the measurement vector after the vector A is injected. It's equal to dA minus H times XA, which is equal to the residual vector before the attack is applied. However, the state estimation result had been changed from activate hat to activate hat plus C. Since C is an arbitrary vector, the attacker can modify the state estimation result fully following his or her mind. So we can see that FDIA is actually a very serious kind of attack because attackers can change the power system state estimation result as he want. So we need to find some solution to defend against FDIA. The first thing is to detect it. Uh, so let's get back to the main thread. In the next section, I will present a new FDIA detection framework, which employs the dynamic neural network paradigm to resist concept drift. Existing deep learning-based malicious data detection model usually consists of a feature extraction component and a classifier component. The model is usually trained in the supervised manner by inputting historical data samples with normal or malicious labels. Internal parameters of the model are adjusted by error back propagation. After offline training, the internal parameters remain unchanged during online operation. When the statistical distribution of the online samples deviates from that of the offline samples, the detection accuracy of the model may decrease. There are both active and passive methods to cope with the concept drift in malicious data detection. Active methods retrain the learning model when significant concept drift is detected to ensure that the model keeps up with the changes in the data distribution. Some common methods include transfer learning and incremental learning. However, this approach suffers from the difficulty of collecting enough samples under the new distribution and the time delay of model retraining. Passive methods, on the other hand, do not actively detect concept drift. They incorporate samples collected under multiple operating conditions during offline training so that model can maintain a certain level of accuracy when the online application encounters a similar operating condition. This method avoids frequent model retraining, but requires feature extraction and generalization capabilities. Our paper proposes a proactive online model updating strategy that combines active and passive approaches. Rather than training the learning model using measurement collected under a single or very few operating conditions of power grids, the proposed method trains the learning model using data collected under many more operating conditions. By doing so, we hope the learning model can adapt to the changing operating conditions of power grid to a certain extent, so that the model can be retrained and updated in the relatively low frequency. Now the question is how to enable the learning models to fully learn the patterns of the data under a large number of different statistical distributions. Dynamic neural network present a revolutionary new meta-learning paradigm that is transforming the data detection. Traditional AI models have fixed architecture and parameters after training, much like the structure of a house that remain unchanged when built. In contrast, DNN or dynamic neural network, we call it DNN, dynamically adjust their architectures or parameters based on the input samples during online inference, which is like a smart home that can adapt its layout to the resident needs. This flexibility enables DNN to better adapt to the complex and dynamic data environments. The proposed method adopts a weight prediction-based DNN architecture, which belongs to the dynamic parameters category. The proposed malicious data detection framework based on dynamic neural network has a two-layer structure. The lower layer is similar to traditional detection models and consists of a convolutional long short-term memory feature extractor and a multi-layer perceptron classifier. The feature extraction module is assembled from multiple LSTM layers with different convolutional kernel sizes, which can reveal the multi-scale spatial temporal features of the measurement data. And the classification module uses a feed-forward multi-layer perceptron. The innovation of the detection framework is primarily reflected in the upper layer. The upper layer DINN adapter is essentially an MLP. Its unique feature lies in its ability to dynamically adjust the internal weights of the last hidden layer of the lower layer MLP classifier during runtime. During the offline training phase, the optimal mapping between the input samples and the internal parameters of the lower layer MLP can be learned. This means that the framework can train an infinite number of detection models for the infinite number of operating conditions, which significantly enhance the adaptability of the FDIN detection framework under concept drift. The introduction of the DINN adapter introduces a branching in the data flow path. In traditional detection models, the feature extractor and classifier can be trained as a whole by minimizing the sum of the loss function. However, this branching prevents the three modules of the proposed framework from being trained simultaneously using the error backpropagation algorithm. To address this, an interactive co-training method based on the EM algorithm is proposed. The interactive co-training strategy consists of two steps, the E step and the M step. In the E step, the error backpropagation algorithm is used to train the lower level feature extractor and classifier based on the cross entropy loss. And then in the M step, the internal weights of the last hidden layer of the lower layer MLP are extracted and used as the regression target for training the dynamic DINN adapter. So by alternately executing the E and M steps, the parameters of both layers can ultimately be trained to converge. Now let's have a look at the experimental validation results. First, we focus on the adaptability of malicious data detection to power flow fluctuations. In case 1, the model is trained with small fluctuation data and is tested with large fluctuation data. In case 2 and case 3, some medium-level fluctuation and large fluctuation data is added to the training dataset, while the model is still tested using large fluctuation data. We can see from the figure that the detection accuracy of the proposed DINN model is higher than the model without DINN, no matter in case 1, 2, and 3. Now let's validate the adaptability of the proposed model to the topology changes. In case 1, the model is trained with data collected under a condition that all transmission lines are in operation, and it tested with data collected under a condition that a random line is out of service. In case 2, the majority of the training dataset is collected under the all line in service condition, only with a small amount of n-1 topology data included. The test dataset is remained the same as case 1, where all data are collected under n-1 topology. It can be seen from the figures that in all cases, the detection accuracy of the proposed DINN model is higher than the model without DINN. So under the condition that the power flow fluctuation and topology changes are both considered, the conclusion is similar. The FDIN detection accuracy with DINN adapter is higher than that without DINN adapter under all test scenarios, which validates the effectiveness of the proposed framework. In malicious data detection, the convergence stability of the training process is very important. As can be seen from the curves, the loss functions of both layers decrease rapidly and achieves robust convergence, which demonstrates the effectiveness of the proposed interactive co-training strategy. Now let's move on to the next section. In this section, I will present a novel bad data recovery method based on diffusion models, which can achieve a better data recovery performance in the case that the data has strong randomness and high nonlinearity. In recent years, several generative models have been proposed in the literature for missing data completion, including generative adversarial networks, uh, also known as GAN, variational autoencoders known as VAE, flow-based models, and diffusion models. Compared with other models, diffusion models exhibit higher stability and better performance, especially when the data has complex patterns. The diffusion model involves two key processes, a forward diffusion process and a backward generation process. In the forward diffusion process, Gaussian noise is added at each step based on the previous step. And in the backward generation process, the reverse denoising process that uses the Gaussian distribution parameterized by a neural network to approximate the target. Here, a neural network parameterization refers that the mean and variance of the Gaussian distribution are predicted by a neural network. The core of the diffusion model lies in training a neural network model during the reverse denoising process to predict the noise added during the forward diffusion process. The denoising diffusion probability model, or the DDPM, which is a kind of a specific diffusion model, the DDPM selects a neural network called denoising unit to predict the noise. A KL divergence is used to measure the deviation between the predicted distribution and the original distribution to guide the training of the denoising unit network so that the denoised samples are highly similar to the original samples before noise were added. And DDIM is a variant of DDPM. DDIM has, compared to DDPM, DDIM has basically the same data reconstruction capability, but much higher efficiency. In DDIM, the forward process is no longer defined as a Markov chain, so that only the satisfaction of marginal distribution is required. But the reverse process using the constant coefficient and square completing method to find the variance. Besides the ordinary diffusion model, which includes DDPM and DDIM, there is also a special type of diffusion model named conditionally guided diffusion model. It can control the generation of data samples by inputting different bootstrap conditions in the reverse process. Conditionally guided diffusion models are often used in the field of image generation. Users can control the style of the generated image, such as oil painting, cartoon, or photograph, by specifying style prompts. Compared with the ordinary diffusion models, conditionally guided diffusion models usually have higher interpretability and higher editability, making it a good choice for power system measurement recovery. Then we can use the normal data retained in the measurement vector as the conditional prompt, as a condition prompt to guide the generation or the imputation of the missing data or FDIA data in the matrix. To achieve bad data recovery, we proposed a two-stage anomaly detection and data recovery framework. The first stage is anomaly detection, using a conditional control diffusion model to calculate the recovery value. The difference is calculated and the 3 sigma test is performed, outputting the anomaly measurement set 1 minus omega. When the anomaly measurement ratio exceeds 10%, the second stage is entered, and the measurement reconstruction is performed on the anomaly measurement set 1 minus omega. During the reconstruction process, the same unit model is reused to fill in the missing position in the anomaly measurement set, and the resampling technology is used to improve the recovery accuracy. Diffusion models suffer from a disadvantage of being time-consuming. To address this issue, an optimal variance strategy is introduced to accelerate the generation process. Optimal variance helps diffusion models determine the optimal generation trajectory, thereby reducing the time consumption. Furthermore, DDIM may reuse a shorter subsequent contained in the original subsequent of DDPM that does not need additional training to form the forward process. If the length of the sample sequence is S, the computational complexity can be reduced to S by N of the original. Now take a look at the experimental result. The first set of experiments focused on the recovery of SCADA data. We compared 5 different data recovery algorithms, including LSTM, ADMM, VAE, GAN, and the proposed method. We test the performance of the 5 candidate algorithms on IEEE 30, 57, and 118 bus systems. The anomaly types include 3 types of FDIA along with data loss. It can be seen from the table that the proposed method achieves the lowest data recovery ever. We also compared the data recovery performance of the proposed method using PMU measurements with high nonlinearity and strong randomness. The result is similar. The proposed method has the lowest data reconstruction error among all the 5 candidate algorithms. We also conduct experiments on the optimal hyperparameter tuning and robustness verification. And finally, we also demonstrate that the introduction of the subsequent acceleration strategy and the optimal variant of DDIM saves nearly 9/10 of the time while guaranteeing recovery accuracy. Okay, finally, let's quickly summarize today's presentation. Today's presentation focuses on malicious data detection and recovery in power systems. Currently, power systems face severe cyber-physical attack risks, such as FDIA. Malicious measurement data significantly impact system stability. Data-driven method offers a new approach to addressing this issue. Based on dynamic neural network, a 2-layer malicious data detection framework is proposed. An interactive co-training scheme is designed using the EM algorithm. The framework can effectively improve the adaptability to the operational condition changes of the power system. Additionally, based on a denoising diffusion model, a 2-stage power system measurement recovery framework is proposed. The spatial temporal correlations in power system measurements can be effectively extracted. The framework achieves efficient outlier removal and missing data filling. Even the data has high nonlinearity and strong randomness. Okay, this is all I would like to share today. Thank you for your listening. Please feel free to ask any question. Thanks.
Thank you for the wonderful presentation, Dr. Wang. Um, so if you have any questions, please utilize our chat windows and then type your questions if you have. And then in the meantime, I have just a very, very basic question for you. So I did not actually expect that you also cover how we can recover the data. I just estimated that you highlighted like a false data injection attack, how we can attack the grid, and then what is the results of the cyber attack. And then, so if you detect the cyber attack, and if you correct the malicious data using the DDIM or DDPM, and then what is the difference between the results, of the results between the use of your technique and then if we do not use that technique? So what is the difference of the results? Do you have any examples of your case studies?
Yes, actually, I have an example in the original paper, shown in the paper, but not included in today's presentation.
Okay.
Actually, the FDIA can only be launched if the power system measurement vector has maliciously modified during communication before the vector has received by the control center to conduct the state estimation application. If we can detect the malicious modification in the data vector and correct that value to make sure that the power system control center receive the correct or approximately correct data. The subsequent state estimation process will not be influenced or impacted by the FDIA. If we can correct the data, the measurement or the abnormal data in the measurement vector, actually the state estimation uh, cannot be influenced anymore.
Oh, I see, I see. So, for example, if the state estimator is compromised, I mean, if the state estimation results will be manipulated, and then if we get the wrong results as the state estimates, and then what is the typical results? Is this like do we have power outages or at the steady state, there is no events, right? So
Yeah,
what is the possible like just an example? I'd like to hear just example scenario, and then the typical impact of the cyber
yeah.
attack.
Yes, actually, FDIA that it attack targeting the state estimation results. State estimation, this is a relatively an indirect kind of cyber physical attack to the power system, because we need the participation of the operators, power system operators, to finalize the attack. How do I understand that participation of operators? Uh, I mean that the we can modify the state estimation result, right, by conducting FDIA. And once the state estimation result is changed to an arbitrarily selected state by the attacker, it can mislead the power system operators uh, to make wrong control actions. For example, if we can, change the state power system state to a state that a severe uh, power outage has happened, but the outage has not happened in the real world. It is, masqueraded by by the attacker. The power system operators may be misled uh, by such state estimation results to conduct some dispatching actions. But that dispatching action may actually cause severe consequences in real world power system operations. That is
Like
how this,
a
yeah,
frequency excursion or something.
yeah, frequent discussion or some, if the operators cut down some critical
Hmm.
transmission line, it may
Okay,
cause some instability of the power system.
I see, I
So
see.
I say the FDIA is an indirect has an indirect impact on the power system usually.
Okay, got it. Thank you for the clarification. And now we
Yeah.
have one question in chat window. Can you open it and then quickly read it?
Yeah, I see, I see. I understood the residual vector method to set a threshold for the magnitude of the R vector. Is this correct? If so, can the phase of the R can also be tracked? Actually, yes, that's a good question. Thank you, Bethan. We can see that slide. Let's get back to that page. Actually, the equation here of the residual vector I shown on the screen is based on a linearized state estimation, which is a simplified version of the weighted least square state estimation. The linearized state estimation, you know, uh, does not, it's just like the DC state estimation. It doesn't focus on the phase part of the power system. It just it has some assumptions. For example, the uh, maybe the power system, the voltage magnitude of the power system is set to 1. Uh, and we only focused on the phase angle part of the state estimation. So it does not, the R here is not a complex variables. It's just a uh, real variables. But in real world, the R can be complex variables. In that case, we calculate the magnitude of R because uh, actually this is a so-called residual-based test. It has I don't know how to you know it, I don't know how to explain it, but it has a strong mathematical proof that this kind of attack can identify the bad data in the residual vector. Yeah.
Okay. Thank you. We have one more question in the chat window.
Okay. Let's see. Has there been severe Yeah, the first question, has there been severe FDI attacks? What scope such attacks, utility level or set level? Actually, in the real world, there has not been an real world FDI attack. FDI attack is only discussed in the literature. It has not happened. As far as I know, it has not happened in the real world. So but it is not at the site level because to conduct FDI attacks, we need to see this page. The attack model of FDI attack is A equal to HC, where H is Merriman Jacobian matrix. A Merriman Jacobian matrix include the data, include the information of power system configuration of the whole power system. The whole the H includes the information of the uh, overall power system, so it cannot be a site level attack. It is a power system, the whole power system level attack.
Thank you. We have two more questions.
Yes, I see that. Are we considering the smart meter state because usually smart meters are connected to the IT side of the utility? Uh, I would say maybe not because actually the method I introduced today the two specific methods including the bad data detection and bad data recovery they are both data-driven method. Actually, they can be applied to any kind of power system data to detect the abnormal data in the data vector. However, the FDIA, the traditional or the you know uh, traditionally when we talk FDIA, we focus on the transmission grid. We didn't focus much on the distribution grid. Smart meters data, they are smart meters are deployed in the distribution network, and they collect the user uh, power consumption data, and they are aggregated they are aggregated before transmitted to the power utility to calculate the bus load. And actually, as we can see here, the FDIA, the attack model of FDIA, A equal to HC, where H is the power system topology and parameters. H includes power system topology and parameters. So uh, what we focused in FDIA is the bus load is a summation of a certain range of the power smart meter data. We didn't focus on a specific smarter meter data measurement uh, in FDIA. But the method I discussed today, the dynamic neural network based bad data detection and diffusion model-based bad data recovery. These two methods are data-driven. They can be applied to a smart meter data to detect the bad data in the smart meters.
Thank you. And then one more question. This will be the last. So, Dr. Wang, can you read it? So, do we protect each power system facility individually? This is the question, right?
Sorry, I didn't see that.
Oh,
It,
okay.
is
Yeah, so
there a new?
I just read that. Do we protect each power system facility individually? This is the question.
Okay.
I don't know. Power system facility means power system equipment.
Power system, what? Sorry?
Y-
Pot,
Yeah, so the question is
could,
something like do we protect each power system equipment individually? I think
and
this question.
can you type the question in the chat window? Because
Oh,
I
I
didn't
think I think the question is between the difference between software and hardware. The analytics between the software and the hardware part of it. So how would you protect the power? I think the question is, how would you protect the power system regarding hardware wise?
how do we protect each power system facility individually? I mean maybe the topics or the methods we discussed today, the two algorithms, are control center level protection. We developed the software and adopt and deploy the software in power system control centers to screen to filter out bad data before the data were sent into the state estimation applications. And we try to detect the bad data in the measurement vectors received uh, at the control center and try to recover the bad data in the measurement vector. So we do not protect each measurement device or each communication channel. We just conduct the protection in the overall or in the general viewpoint.
yeah, I agree with this. But essentially, we use a kind of dedicated the communication system to ensure the security of the protection devices. And
Yeah.
then, so if we have like a bus or transformer, and we have corresponding individual protection devices each. So, but anyway, your topic is like how we can manipulate the state estimator. This is a kind of like dispatching center levels, right?
Yes.
Okay. Yeah, but so if you can manipulate something, and then for example, let's say we are like a hacker, and then if we manipulate the state estimator, but in this case we can directly the control the power equipment. We can facilitate the grid operator to do something, right? But if we
Yeah.
can attack a particular like a protection devices directly, and then we can directly disconnect some of the equipment. So have you ever tried this kind of studies before?
Actually, no, because that kind of attack I think does not belong to the FDIA part,
Mhm.
FDIA range. It just you know, if we are a very strong hacker, we can directly cut down the operation of some critical device in the power system. Actually, this is what happened in the Ukraine blackout. The attackers infiltrate into the substation control system in Ukraine and cut down some critical line. So the blackout that happened. It does not caused by FDIA model, but caused by exactly what you have described just now. Uh, the attacker just cut down the critical lines.
I
So
see.
I think this kind of attack is is exactly a very uh, very important topic in power system cybersecurity, but it may require some device level protection or device level monitoring and bad data detection techniques, but it's not what we focused in the FDIA, which is a system level attack prevention strategy.
Okay. Yeah, thank you. I think time is almost up. So let me quickly introduce the future webinar this time. So everyone, the next webinar will be held sometime in September next month. And we're going to invite a professor from Brazil who is currently a vice chair of the IEEE Power System Dynamic Performance Committee to showcase the Brazilian Black Hat event caused by inverter-based resources. And then the flyer will be uploaded to the IEEE 40th section website. Then please tune in to everyone. Can you hear me?
Yeah.
Now, Koji, can you repeat what you said?
Yeah. So can you share your slides with us?
No, Koji, you mean you share your screen or?
No, the slides.
We didn't see. We didn't see your slide. I maybe I need to stop
No.
my
Yeah.
screen share.
I'm saying that. So I would like to receive your slides if possible.
Yeah, my slide is I can see my slide.
No. Koji's asking you, can you share your slides? Can you please share your slides with us? You know, like meaning that, can you send us your slides?
Oh yeah, of course.
Okay, perfect.
Yeah.
So yeah, please do this for us, and then I can upload your slides to the Footier section website.
Okay.
Then, yeah. Thank you, Dr. Wang. And then, so I think you have another appointment starting at 8 a.m. local time, right? So yeah, please enjoy the rest of your day.
Thank you, Koji. Thank you for having me in this webinar.
Yeah,
Thank you
perfect.
very much. Appreciate it.
Yeah.
Yeah, bye for now, everyone.
Bye bye.
Thank you, Koji.
Yeah, thank you, Max.